To make this completely concrete, RFC 3526 specifies this particular P, which is a 2048-bit number. And we use this P with G equals 2. So this P with G equals 2, that's kind of the yellow paint. Let's try this in some Python code here. So I've written down that same P and that same G from the slide. And then I'm going to make Alice's secret by calling Python's random range function to say give me a number up to P minus 1. I don't want to get 0, I need something bigger than 0. So that's why I go P minus 1 and then add 1 more to the end. So I get a number up to P minus 2, and so adding 1 gets me a positive number up to P minus 1. The same for secret B, and then I'm going to take G to the secret A power modulo P. So I can't just take the exponent and then do the modulo. I need to do exponentiation and modulo at the same time. So that's the xmod function. And then that is the secret that Alice would be willing to give to Bob. And this is the secret that Bob would be willing to give to Alice. And then Bob will take that public information from Alice, do xmod again with secret B and P, and we get A and B, and we should end up with A and B as the same. Let's try running this. I'll run Python and then import that code. And you can see that the shared secret was printed out, so that's the number that both Alice and Bob arrived at this time around. And the assertion passed, meaning that Alice and Bob arrived at the same shared secret. Just for completeness, here is how you would implement modular exponentiation if you had to. This is the divide and conquer, where if we get down to less than a power of 2, then we just use the plain old power function for exponentiation. Otherwise, we recur with halves and do the modulos along the way. But it turns out that Python's POW function actually accepts this modulo m as a third argument anyway. This code below illustrates that Diffie-Hellman is really straightforward as long as you have the libraries that'll compute with big numbers for you.